How is that? Okay, so today's main topic is classification. So we're going to look at classification again, building on the notion of vector space models. So we will study two classification algorithms that work based on a vector space representation of the data. So since our main way of representing data and classes in this lecture is going to be vector spaces, I'm going to do a review of the things we have looked at last week. If you have any questions, you can ask now, just to make sure that we all understand what we mean by vector space and feature vectors, dimensions, etc. So last week we looked at the semantic spaces. That was sort of the overall theme of the lecture, which is vector space models for distributional semantics. And vector space models are these algebraic models that are used in general to represent data. And distributional semantics is based on the distributional hypothesis, which is if words share the same context, these words are expected to have similar meanings. And we represented words as points or vectors in our vector space. And the positioning of these points or vectors is dependent on or is based on the occurrence counts for various context features. And we introduced different ways of defining what is a context. So a bag of word context is all the words occurring with a given term in the same sentence, in the same paragraph, etc. Words to the left and right of the target word, etc., etc. And then you have, for each word, we would extract the context features from a large collection of text, normally called corpus. And each feature type would refer or would correspond to a dimension in our vector space. And then each word, OI, is represented by sometimes or length normalized n-dimensional vector xi, which has n elements. Again, each of these elements is corresponding to a value on a dimension in our vector space. So this notation here we're going to reuse over and over. So just not to be confused when we refer to a word, OI, so that's the word itself or the object itself, but it's represented by a vector, xi. So you'll often see on the slides later on that we talk about an object OJ that is represented by a feature vector xj, which has n elements. And then we, based on this sort of representation of words, we introduced two similarity measures, the Euclidean distance and the cosine similarity measure, which is based on the angle between the vectors. And then the overall story became that if we can approximate semantic relatedness in a sense using distributional similarity, the distributional hypothesis, and the distributional similarity can be approximated through looking at spatial proximity, so Euclidean distance and again cosine similarity. So yet another visualization of just to make sure that you understand this. So this is a vector space here, 3-dimensional. So each of these dimensions represent the feature. So you have bake is a feature, share is another feature, and eat is the third feature. And we have 4 words. We have taxi, cheese, cake, and bread. And as you can see, the word taxi here has a high value on the share dimension. So that's the dimension for the feature share, because you expect sharing a taxi, so you share a taxi with someone, to be very common or to be somewhat common. In contrast to eat and bake, where you see it has almost a 0 value on that, because it's less likely that you would eat or very unlikely you eat or bake. And then you move to cheese and you see that it still has a high value on share, because you can still share cheese and you can eat it, so it has a higher value on the eat feature dimension, but less on the bake, almost 0 also. And then finally you have cake and bread, which you can share, eat, and bake. So that's sort of basically the sort of a simplification and a visualization of how you can represent these four words based on their context. Any questions on this part? Do you feel that you're missing something, that you're not following? Yeah. Mm-hmm. Yeah. So yeah, I'll just repeat the question just for the recording. So you're saying that summarizing what you said is that looking at the meaning of a word like bread in a small corpus will not represent the real meaning, whereas if you look at a large corpus and millions of books, not thousands, then this would give you the real representation. That's true. So and that's in general this concept of having more data. So the more the merrier in such applications. The more data you have, the more realistic representation you have. So what we give you in the in the second assignment, 2A, which you probably have looked at, is this a sample of the brown corpus of about 20,000 sentences. This is by no means a large corpus. We normally work with millions or sometimes billions. So of course, so what you're saying is correct. Is that how do you, with more data you approach a more realistic representation? And so just another way also to think about vector space models. So far we have been looking at vector space models for detecting words and with their for detecting words with similar meanings. So, but as we mentioned before, vector space models are general algebraic models, so or geometrical models that can be used or are in fact used in many other applications, and they originate in IR. So, in IR is the information retrieval field of study, and the sort of I'm going to present how we actually work with vector space models in IR, information retrieval, for two reasons. One is because the readings you're doing now is from an IR book, a book about information retrieval, and two, because it might also help you understand more if you look at the problem from a different angle. So in IR, we are interested in finding documents with similar content. So not words, but rather documents. So when I say IR, you can immediately think of search engines. So when you search something on the internet, you're writing a query, and the returned result is a set of documents. And these documents are web pages, right? So we can use vector space models to represent documents. And so now each document, DJ is represented by a feature vector. But now the feature corresponds to the terms occurring within the document. In IR, we use term instead of word, or token. So they usually use term, which basically words. So it's all the words occurring in the document itself. So all the words in a web page make up the feature vectors, or the features for that document. And then we can apply then the same concept. So we have represented our documents as vectors, and we can say that spatial distance is more or less corresponding to similarity of content. So, and the query you type, it can also be represented as a vector. And so you end up with a situation like this on here on the right side, where you have a document DA represented as a vector, document D2 represented as a D1, sorry, D2, and that's your query. And the closer and then you measure the distance or the cosine similarity, and the closer these vectors are to your query, the more relevant they are. So that's basically sort of the gist of it. You don't, it's not part of the course, but it's good to see how it works and how you can relate what you learned to another application. One other thing, so also if you remember from last lecture, we said that raw frequencies are not always the most indicative or discriminative kind of features. So if you just depend or rely on the raw counts of how many times a given word occurs with some features, that's not always the best to actually represent features. So an alternative to this that is used in IR is a weighting function called TF-IDF. And TF-IDF stands for term frequency inverse document frequency. So term frequency, so it's two parts. So first you have term frequency. What do we mean by term frequency? It's simply the number of times a term occurs within a document. So it's this function here, TF, that takes a term TI in a document DJ, and it counts how many times a term occurs within this document. So that's basically just frequency count. And then you have the inverse document frequency. So first we start with the document frequency. What's a document frequency? The document frequency is how many documents, or the total number of documents in our collection where a term occurs in. So when you work with IR, you're working with a collection of documents. So the web, the internet, everything on the internet, so millions of documents. And the DF here, the DF measure or the DF function, counts how many documents in your collection have a given term. So intelligence, for example, and you have 20,000 documents. How many of these 20,000 documents have the term include the term intelligence? And then the inverse document frequency, so is based on this document frequency, which is defined as the logarithm of the number of documents in the collection divided by the document frequency. So the final function would then be the multiplication of the term frequency and the inverse document frequency. And the idea behind this, why this kind of weighting function would work. So let's take two words. So let's say we're looking at artificial and we're looking at the pronoun I, for example. So if you want to weight it for a given function, so you count the number of times it occurs within for a given document. You count the number of times a word like I occurs in a document, so say 20 times. And then you want to compute the IDF, the inverse document frequency. And then you expect a word like I, or a pronoun like I, to be in all of the documents in your collection. It's a very common term, right? So the value here would be, if we have 20, so in the inverse document frequency, if we have 20,000 documents in our collection, so n will be 20,000. And the document frequency, if it occurs in all the documents, it will also be 20,000, right? So 20,000 divided by 20,000, that's 1. And the logarithm of 1 is 0. And so the weight will be 0. And why is that? Because a word that occurs in all documents is not a discriminative feature, is not an indicative feature of the content of the word. So you compare it to a word like artificial, which occurs in 10 out of 20,000. This should be an indicative or a feature that gets more weight. And that's what happens here in this function. So the overall picture then is that a high TF-IDF is obtained if a term has a high frequency in the given document, but a low frequency over the whole collection of documents. And so with this measure, then we actually are able to filter out all the common terms. So even if you don't do stop word removal, they will fall out by this definition of the weighting function. So yeah, that's more or less it in this regard. I think it's again, this is not the core principle in what we are working with, because we're not working with documents and we don't have this sort of concept of collection of documents, but it's a neat way of trying to give more value to indicative features or discriminative features, in contrast to very common words that do not add more information or more sort of ability for the classifier or the model to distinguish between different objects or data points. Okay, so that was it about the overview or the reminder. So today, as I said, we're going to look at classification, which is a task that's part of machine learning. So any guess, any idea what is classification? Just a simple example, or you go. Yeah. Try to find clusters of similar data and classify them. Yeah, and yeah, okay, that's an example. So trying to find clusters of similar data, that's clustering. Sort of, if we don't have predefined classes, and will be in our topic for the next lecture. Spam filtering is an example of classification. It's basically you have data points and you want to objects in general, abstract object, you want to classify them into different classes. In this example, the classes will be spam, non-spam, or spam legitimate email. We'll look at this at a more sort of detailed example of what is classification. So, but this is more or less our sort of topic for today, classification. Then we'll look more closely on how to represent classes in a vector space model again. So we work with words, single data points. Now we're working with classes, a collection of points, a collection of things. How do we represent them in a vector space model? And what do we mean by class membership? So when is a point a member of a class, etc. And then we'll look at two examples of classifiers. Simple classifiers, powerful in some tasks, but easy to understand and sort of easy to implement. So Rocchio classifier and KNN, K nearest neighbor classifier. So classification, first of all, in machine learning, there are two general tasks or categorization tasks. One is called classification and the other is clustering. So classification, if we start with classification, it's an instance of supervised learning, what we call supervised learning, and it requires labeled training data. So and our aim in classification is to train a classifier to automatically assign new instances to predefined classes given some set of training examples. So what does that really mean? So we have a set of we have a set of training examples, meaning that we have, let's think of documents. So we have a set of documents that are annotated with topics. So this document is about politics, that document is about sport, etc. So again, 10,000 documents, for example. And we want to, this is what we call the labeled training data, because it's labeled, we know the true outcome of each of these, the classification of each of these documents. And we want to train a model, a classifier, that is able to look at a new document that is not part of our data set and assign a topic to it. So, and that's so the definition here says new instances. So if you think in terms of this example, these new instances are new documents, and assign them to predefined classes. So we have predefined set of classes. So we know that there are 10 topics that our documents can be part of, and a new document will be assigned to one of these 10 topics. And the reason, and of course the classifier will then be looking at the training examples and trying to measure some features to learn the differences between these classes. And the reason, of course, why we say this is supervised learning, because we have this set of labeled examples. This is essential here, is that it's supervised because we give it instances of the things that we wanted to learn. So it has been annotated by human experts. Clustering, on the other hand, is an instance of unsupervised learning, and it starts from unlabeled data. And the goal then is to automatically group similar objects together. So instead of giving the classifier a set of documents that are already annotated with topics, we just say, here is a set of documents, find the similar ones and put them in groups. And so we don't have any predefined set of classes or structures. We just specify a similarity measure. What does it mean for two documents to be similar? And when do they form a group together? So that's going to be the topic we'll look for next week. So we'll look at it in more details. But supervised and unsupervised, then sort of this is the main distinction here, is that supervised unlabeled data for clustering, unsupervised unlabeled data for clustering, supervised and labeled data for classification. So if we go back to this email spam example, so how do we actually design an automatic spam detector to do the classification? This is something that's sort of, it's a textbook example of what is classification, and we all have it in our mailboxes nowadays. So it's easy to explain, just to show what it means to do classification. So normally you would have a set of emails that were tagged as spam or email. So set of messages saying that this is spam and this is email or legitimate email. And you would extract features that are that help the classifier distinguish between what are spam emails and what are legitimate emails. And these features could be as simple as, for example, frequency counts of words in spam emails. So a word like money or free or you, instead of just using your name, this would have higher frequency in spam emails. And also you can look at the frequency counts of punctuation marks in spam emails. So overuse of exclamation marks or inconsistent use of punctuation marks could be an indicator of an email being spam or not. And then, of course, what you will need is the learning algorithm or the model, so that you feed in the data with the annotated training examples and the features, and your model is expected to distinguish between when an incoming email is arrives in your inbox, then it will be able to tell what's spam and what's not. Other examples, we have something called named entity recognition, which is the task of assigning abstract semantic concepts to proper nouns in sentences. So I think I have an example here to show. It's easier to. So here, this is just a demo I found online. So here we have this sentence that is the Mona Lisa is a 16th century oil painting created by Leonardo. It's held at the Louvre in Paris. So we can extract entities from this sentence and classify them. So here, for example, the Mona Lisa is a work according to this implementation of named entity recognition. Louvre and Paris are called places. So assigning these kind of abstract semantic concepts or classes to words within a sentence is a task of classification. First, you identify which words within the sentence are candidate named entities, and then you classify the type of that named entity. Is it a person? Is it an organization, a place, etc.? And then another topic that we actually, or another example we talked about is this document classification, document topic classification. So classifying documents based on their topic. So a real life example of this also is Google News. So you go to Google News and it will aggregate and classify different news pieces under different topics. Authorship attribution, so that's where you classify the text based on who is the author. So you use stylistic features and etc. Sentiment analysis, we also talked about this before in the course, is this task of classifying whether a piece of text, being a tweet or a paragraph or a full document, whether it's negative or positive, and there are different coarse or fine-grained levels of being negative and positive. It's used in, yeah, it has different applications in marketing, politics, etc. So these are all examples of classification. So that's sort of a way to understand what we mean by classification. What we will look at today, as I mentioned before, are two classifiers, Rocchio and KNN. They can be used with these applications, but there are also other more powerful classifiers that are based on probabilistic representation of the data rather than vector space representation, just as we're doing here. But we think that these two classifiers are still sort of they're still powerful, but they're also easy to grasp. So that's why we chose them. But they are by no means the only classifiers that exist in machine learning. And they can be powerful for some tasks. So KNN can be powerful for handwritten digit recognition, but not all applications will be solvable or efficiently solvable using these two algorithms. Okay, so that's it for sort of what is classification. Now let's look at what do we mean by a class, and how do we represent a class in a vector space representation? So the class itself could be thought of as a collection or a group of objects. And what we have been doing so far is representing points or objects in a vector space. So if we have this two-dimensional space here, the X's, the circles, and the diamonds here are representing objects in this two-dimensional space. Now, if we think again in this geometrical representation of data, the classes could be represented as regions within the vector space. So this region right here is the class of China. Or documents. So sorry, I didn't explain the example. So this example is, these are documents. So all of these are the documents. The X's are documents about Kenya. The diamonds are documents about the UK, and the circles are documents about China. So these are document topic classification tasks here. And you can think of this class then as a region of within our vector space. That is what we mean by a class. And in order to be able to do vector space classification, we're gonna have to sort of assume that the contiguity hypothesis holds all the time. And what do we mean by the contiguity hypothesis is that the objects that belong to one class, to the same class, form a contiguous region in the space, and the regions of different classes, they don't overlap. So this is what we call a contiguous region because there is no split in it. And as you can see, there are no diamonds sort of in the middle of the circles. So these are two classes, they are so separated, and they form contiguous regions. So this is just an assumption, or it's an hypothesis, sometimes called also the cluster hypothesis, that things that are similar tend to be in the same place. That's basically it. So things that have similar features tend to be in this similar region in the space, which we also take as classes that are objects that are representing or belonging to one class tend to be in the same region in the space. Yeah.
Does that mean that one object cannot be in several classes?
No, that doesn't mean that, though. You can have an object belonging to different classes, but it will violate this assumption. But of course, we'll come to this in the next slide. What do you mean by class membership? And you can actually define class membership as an object being a member of one class only, and you can also define it as an object being member of different classes at the same time. But if we allow that, then the contiguity hypothesis won't hold for this. So we just make it. We have this hypothesis so that we can work with vector space based representation for classification. Yeah. Yes, and you can do that, and that's you're just so many steps ahead in the in the lecture. We're going to talk about KNN, and we're going to talk about one way of doing that, which is basically saying that a document is part of two classes, and yeah. So we're gonna look at that later. I think it's just easier to look at it again in the end, and if you have a question, we can consider it then. Yeah, and so given this representation and this contiguity hypothesis, classification then is actually amounts to computing the boundaries between the different classes. So this line here that separates UK and Kenya from China, this one here is called the decision boundary. So the decision boundary is a boundary based. Why is it called decision? Because if a point occurs on the left of this boundary, this one here, I don't know if you're seeing so the one of the boundary of China, then this point that is on the left belongs to the class of China. If it occurs to the right, it could be UK or Kenya. So the decision boundary is just a representation of the boundary that delimits where the class is in our region. And the classification task basically is how do we compute, how do we come up with these boundaries? How do we find them? How do we represent them? And in the boundaries themselves, so the way they are drawn, can be influenced by how we choose to represent our class mathematically. So we still haven't talked about how we represent the class in terms of vectors. So this is still just a conceptual representation. It's a region. So the way we choose to represent the class is also has influence or has consequences on how these boundaries are drawn. So more concretely then, how do we actually represent the class? So we have a set of points, a set of feature vectors representing or belonging to one class. How do we come up with the representation saying that these documents are represented by this vector or this set of vectors? So the first example or the first way of doing this is called exemplar-based representation. So an exemplar-based representation, what we do is we simply don't represent the class. We don't represent it, meaning but that we say every member that belongs to this class is a representative of the class. So as it said here, there is no abstraction, so we don't compute anything. We just say all the vectors that are annotated as China documents are representative of our class, and this whole collection of points is what we will call the class. So this kind of representation is used in so-called something called instance-based learning or memory-based learning, and KNN is an example of this. So if you are points in the class that is in 4820, each and every one of you is a representative of the class. So in a sense. Whereas in other examples, as we will see, we'll try to find one representative, one single point, one single data point, or one single student or abstract student, as we will see, that is representative of the class itself. So to take this one step further, we can think of something called medoids. Medoids is a wordplay on medians. So if you know what's centroids, medoids is based on medians, a wordplay on medians. But anyway, so medoids is what it means is that we want to represent a class by a single member that is considered central. And what do we mean by central? Is the object with maximum average similarity to other objects in the group. So if we think again about this document classification example, so all the documents that are part of the class China, we want to pick a document of these examples that is most central to the class. And what do we mean by most central? It's the document or the feature vector that has the highest or the maximum average similarity to all other documents in the class. So we compute pairwise similarity with all other elements or instances in the class, and we find the object or the instance that has the highest average similarity. So and that would be the representative of our class. So this is then this instance would be the representative of the China class, for example. Another way to represent the class is what we call centroid-based representation. So centroid-based representation, we look for, we compute the average, or what we call the center of mass in the region. So instead of picking one instance from the set of documents as in the medoids, we pick we compute the average of all the instances or the vectors that belong to a class and say that this is the representative of the class. So given a class CI, where each object OJ being a member is represented as a feature vector xj, we can compute a centroid, the class centroid mu I, as the sum of all vectors that belong to this class divided by the number of vectors within this class. So this is how you compute the average vector. So both centroids and medoids, they are trying to represent the group of objects by a single prototype. So a prototypical vector that represents the class. But in medoid, we are looking for an actual member of the group. So we're looking for an actual document that is part of the group which has the maximum average similarity to all other members. Whereas in centroids, it's an abstract vector. It's an abstract instance that is computed by averaging all the vectors in the class. Is the distinction clear? Do you? So, and in both cases then, when we have this prototypical representative of the class, whether it's an actual member or not, we are introducing this concept of typicality. So, and typicality can be defined by computing a member's distance to the prototype. So, the further a document is from the prototypical vector representing the class China, the less typical this document is. And we can also play with the sort of, if we take this typicality notion to be correct, meaning that there is actually a typical member of the class, we can then augment the centroid computation with distance weighting, meaning that for each member's contribution to the average will be determined by its pairwise similarity to other members of the group. So in this equation here, all members are added together, so they sum together and then divided by the number of the total number of feature vectors. We can add a parameter just before the xj here, that is based on the distance or the average similarity of a given instance to all other instances. So if this instance is completely different, it's far in the feature space from the rest of the group, then its contribution to the average, to the centroid, will be lower. So that's one way of augmenting this this way of the computing or centroid computation. Now this whole discussion of what's a prototypical representative of the class and a group of things is not only in machine learning or in classification, it's in linguistics and philosophy, psychology. It's called the prototype theory. So if I ask you to give me an example of a typical piece of furniture, you're more likely to say a sofa or a chair than a telephone, for example, or a stool. So we kind of think of objects as being more prototypical of members of a group or of a class of things. A penguin is less prototypical example of birds, for example. But there are also other views on this issue saying that we don't actually give examples, we just have a set of attributes, and if an object possesses one of these attributes or has one of these attributes, then it's considered to be part of the class. Yeah, this is just an aside note, just to see that this discussion is not only limited here in the domain of classification and machine learning. So now we know how to represent class. It could be either medoid or sort of all members are part of the class, or a centroid. Now we want to discuss what is actually class membership. How do we define a class, an instance is a member of a class or not? So there are two ways of looking at this. And here, one is the hard classes, and here the membership is Boolean. So an object is either a member of a class or not. So there is no other way around this. So a document is either about China or not. So this is a crisp membership function compared to a fuzzy membership function we'll look at later. But you can also have a variant, which is this disjunctive classes, where objects can be members of different classes or more than one class, but their membership in each of these classes is still hard. So it's still a member of this class. It's an either or. Now you can contrast this to soft classes. So soft classes, the membership is a graded property. So a document is a member of a class about China to some extent, and a class about the UK to some other extent. So it's no longer either or. There is distance weighting, how far it is from the class prototypical representative. And there are two ways to introduce this. So you can there is a probabilistic way and a fuzzy way. And the probabilistic way, the degree of membership is of course restricted between 0 and 1, and the sum of all class memberships for a given object should be 1 in order for the probability to be true here. So a document is a member of class China by probability of 0.4 and UK 0.6. Fuzziness, on the other hand, or fuzzy membership, is again also restricted to 0.1, but without this probabilistic constraint on the sum, meaning that it can be a member of China by value of 0.6 and UK by 0.6. Yeah. Sorry? That's not member of any class. Well, that's the object you want to classify. No? Well, I mean, if you take this example of document topic classification, normally sometimes people would introduce an other class, which is sort of everything else that's not member of any of the classes that we have. But I mean, the question is really dependent on what we are working with, because in the end, so in the classification task, your end goal is to find a class of a given instance or a given object within a predefined set of classes. So you will need to take a decision without giving back that. I mean, it won't be useful if you can't actually take a decision, right? But from theoretical point of view, you can say that there are documents that can't be represented in any of these classes, but you can also look at it from another perspective, saying that even though this document is not part of China fully, as in the hard membership, here comes the fuzzy part of it. So it could be 0.1 member of China and 0.1 member of the UK class, etc. So that's yeah. Yeah, just very quick note on how to, if you want to, to understand the difference between probabilistic and fuzzy membership is, if I say the following sentence, he is somewhat old and he is probably old. So if I say in the first one, when I say he is somewhat old, I mean that I met a person, I talked to him, and he is old, but to some degree. So he's somewhat old. So that's fuzzy because I don't know how sort of if he is a sort of a pretty prototypical member of the class of old people, and then contrast that to he's probably old. And probably old, I actually don't know. There is a chance of 0.4 that he's old. I only talked to him on the phone, and he sounded like an old person, but I don't know. So then maybe I'm saying he's probably old. So that's sort of the difference between this sort of not a very scientific way of explaining it, but it makes it easy to relate. Okay, so we'll take a break now, 15 minutes, and we'll be back. Okay, so we now have a conception of what's a class, how do we represent it, and what do we mean with the different membership functions and class membership functions. So we're ready to look at our first classification model or algorithm, the Rocchio classifier, which is also sometimes called the nearest centroid classifier or the nearest prototype classifier. So in IR, it's called Rocchio classifier, and it's Rocchio is the name or the last name of the person who's invented this algorithm. So as the other name suggests, nearest centroid classifier or nearest prototype classifier, Rocchio uses centroids to represent classes. So for each class, Ci, Rocchio represents this class by its centroid, mu I, which is again computed as the average of the normalized vectors xj of its members. So it's as simple as computing centroids for each class. So the Rocchio algorithm will, given a set of training examples, n classes, so these training examples belongs to n classes, it will compute n centroids and then represent each of these classes by its centroid. And to classify a new object, OJ, which is represented by a feature vector xj, Rocchio will determine which centroid, mu I, that xj is closest to, and then assign that class to the assign that object, the unlabeled object, to the corresponding class. So it's if we want to split the classification in Rocchio into two steps, first training and then the actual classification. Training consists of computing the centroids for the classes. So it's a set of documents. Again, it's just the easiest example. A centroid for China, a centroid for UK, a centroid for Kenya. Now we want to use this classifier, so we give it a feature vector. Before.
Is this centroid recalculated after xj is added?
That's no. It depends on how you define the problem. So there is something called online learning, for example. If you trust your classifier and you add the new classified object to your class, you can recompute it. But normally, or not normally, but I mean, it's also the case that you pre-compute the centroids, and that would be your model, and just classify. They won't change. You won't add new members to the class. Especially if the members or the training data that you have was produced by humans. So people sat down and classify the different documents, then you trust that this knowledge is accurate. When you start relying on the output of the classifier itself, then you no longer have reliable data that allows you to compute the centroid. Yeah. Yes, that's also true. So if you So if you update it after each document is one thing, and if you update it after a batch of documents, that's another thing, right? Yeah. Yeah, that's true. So it will have an effect on the centroid, and that's we restrict ourselves to looking at gold standard data, what we call gold standard. That's data that someone has or some people have, human experts have created, but it's a legitimate, also legitimate approach to recompute. And actually, again, with this question, you're also referring to things that we'll look at in clustering. So in clustering things, we will be also relying on a notion of centroids and recomputing it. But let's keep that for next lecture. Okay, so what I was saying is, so the training is basically just computing centroids, and the classification is given a new object, computing the distance to all of these centroids, and then assigning the class of the closest centroid to the new object. Very simple. That's one of the simplest classification methods, but it's somewhat powerful. And the centroids themselves, so that the algorithm computes, will then define the boundaries of the class region. So remember we talked about that the classification is this definition of decision boundaries, and the centroids will define the class regions and hence the decision boundaries. So let's look at this example here. So how does a Rocchio classifier define a decision boundary? So the decision boundary defined by Rocchio between two classes is defined as the set of points that are on equidistance or equal distance from the two centroids of these two classes. So let's look at this example here. So again, the circles are documents representing class of China, X is Kenya, and diamonds are the UK, and these solid points here are the centroids. So the line here, so this is a two-dimensional space again. So we have, it might be sometimes confusing to think that this is three-dimensional. This is two-dimensional, and these are the decision boundaries. And the decision boundary here that is defined by Rocchio based on the centroids that are computed is the set of points, the line, that has equal distance from the centroid of UK and the centroid of Kenya. So this line here, A1, you can see this A1 that goes from the centroid of UK to the decision boundary, and the line that goes from the centroid of Kenya to the decision boundary A2, they have the same length. So this is how Rocchio will define a decision boundary. It's the set of points in a two-dimensional space. It's a line. In a high dimensional space, in a three-dimensional space, it will be a plane, and higher dimensional space to be hyperplane. So the hyperplane, which contains all the points that have equal distance to the centroids of two classes. Of course, the outcome, so what Rocchio computes is just these centroids, right? So they don't compute, Rocchio is not computing the lines here, but it's an outcome of this computation of the centroids that you can represent the decision boundaries as lines here. These are linear decision boundaries. And an object like, or an unclassified object like the square here falls under the decision boundary that belongs to Kenya. So it will be, we're sure that its distance to Kenya is smaller than its distance to the centroid of China and the UK. Yeah, I think I've said everything to be said here. So this is just the important thing to remember here is that these decision boundaries are linear. And so if we look closer at how Rocchio computes or does the classification and computes centroids, we'll see many problems. The first one is that the classification decision ignores the distribution of members locally within the class, and it's only based on the distance to the centroid. So as we said, the way to classify a new object is to look at the distance to, or to compute the distance to the different centroids, and assign it to the class of the closest centroid. So in other words, when you train a Rocchio classifier, you are given a training data set, you compute the centroids, you store the centroids, and then you no longer care about these training examples. What matters to you is the centroids. And in a way, then, the Rocchio classifier is ignoring the original distribution of the points in the space, which will make it miss on some information. Rocchio also makes this implicit assignment that assumption that the classes are spherical in shape and they have similar radius, so they are for similar size. So if you have a class that's stretched out or spread all over the space, then it's Rocchio will have problem in classifications, and it does not work well. Again, yeah, that's the same thing. So, or actually, that's not exactly the same thing. We'll look at more visual examples of what I've just described here. And then the last thing, which is also very important and sort of a core definition of the Rocchio algorithm, is that it's an algorithm that works on linearly separable data, or linearly separable classes. So if we look again at this example here, it is possible to draw a line that separates the points that belong to the UK class from the points that belong to the Kenya class. So this is a set of linearly separable classes. There are cases where you cannot actually draw a line and separate these points. So when we look at the example of this. And this is where KNN comes into the picture also, when we start working with non-linearly separable classes. So just to make these things more, what I said, just more concrete, let's look at these visual examples. So this is, here you have points that belong to class A on the left. The solid circle again is the centroid of class A, and you have B here, again objects belonging to class called B. The centroid is this red colored circle, and this line dividing here is the decision boundary. It's the set of points that are on equal distance to both centroids, the two centroids of the two classes. So this is what we call an ideal situation for Rocchio, the ideal distribution of data points, because the shape of the class is more or less spherical, and they are more or less of a similar size. And when you are given then a new object X to classify, it will be assigned to class A based on measuring the distance to the centroid, right? So this is how we're going to classify now. We look, and you can guess from just looking at it that it's closer to the centroid of A than to the centroid of B. So it's gonna be assigned a class A, and this looks right. Here's another situation then. Now our classes are not spherical. For some reason, we chose features that ended up representing the members of class A in this elongated, stretch out way, and the members of class B in the same thing. But as you can see, the centroid is still in the same place. So the centroid is still the same. And now when we want to classify with only measuring the distance to the centroid, X will be part of class A. Again, this is how Rocchio works. It only cares about the centroids. It's not looking at the actual data points. And if you look at it as a human, you would think, okay, this looks more like a B than an A, right? So the X here it seems like it's an extension of the way the B points are distributed. So it should be a B. But in this case, only because Rocchio doesn't look on how the points were originally distributed, it just looks at this prototypical representative of the class, it will end up classifying this in the wrong way. Another example where Rocchio will fail is when you have non-contiguous regions. So this is a class A that has two regions in the space. This could be an example of what we call multimodule classes. So classes that consist of different region in the space. So if this is document representation and this class here A is referring to the country that's known today as Myanmar, but was used what was called before Burma. So you could have this representation, right? Because some of the documents will be grouped under the word Myanmar first, and then the documents before the in 1980s it would be under Burma, and then you have suddenly two groups representing the same thing. It's still the same country, but it has two different regions in the space. But in any case, the centroid will end up being, after computing the average of these points, will end up being here, and again X will be belonging to this class, even though it looks like it's part of class B. Also, the other problem, again, that if class A is very condensed and class B is stretched out in still a spherical shape, but of a larger size, again, by just computing the distance to the centroid, the Rocchio classifier will end up assigning class A to X here. So these are just sort of visualizations of the problems that we have mentioned before. That Rocchio assumes a spherical, similar sized distribution of the data in order to work properly. Now the nonlinear problem. So this is a case where you have two classes that are not linearly separable. You cannot draw one line here that is able to separate the points that belong to class A from the points that belongs to class B. So there is no such line here. So it's just impossible. So this is a case where Rocchio will fail because the decision boundaries that it draws are actually linear. So here we will have to look at algorithms like K and N that are able to handle non-linearly separable non-linear boundaries. Sorry. But before that, let's just a quick comment on how about linearity and non-linear boundaries. So if you have this representation of class A and B, now we're working with one dimension. Again, these on one dimension only. The points in class A and B are not separable using one dot or one point. So you cannot find a point. You need 2 points, right? So one here and one there to be able, but that's not linear in a sense. But we are able to actually make this class of, or this classes A and B linearly separable by projecting them or by mapping them to a higher space. So here we are on one-dimensional space, but if we map the points to a higher space, a two-dimensional space, then we are suddenly able to actually draw a line here that is that separates the two classes. And we can do this by basically saying that each point in the previous one-dimension representation will have now an additional value on the y-axis where the value will be the squared of x. So y is the squared of x. This is just an aside note, but this is what we described here is the projection to higher dimensional spaces is the core concept or the basis for something called kernel methods. So kernel methods are used in machine learning where you can map objects to or data points to higher dimensional spaces and make them linearly separable, and then use linear classification methods. Not part of the course, but it's a very powerful trick, again, to sort of be aware of. Okay, so the second classification method we're looking at today is the K nearest neighbor, so K and N. It's an example of memory-based nonlinear classification. So memory-based, we talked about this at the beginning, is the exemplar-based representation. Each point in the class is a representative of the class. Each member of the class is a representative of the class. And nonlinear because it draws a nonlinear boundary between the classes. So let's go through an example to see how this algorithm works. So if k, so in k and n is if k is 1, the algorithm is basically looking for the one nearest neighbor to a given object and assigning the class of that neighbor to the unlabeled object. So if you have a new document you want to classify and you have your training set consisting of 10,000 documents, what you would do is you compute the distance between the unlabeled document to all the documents in your training set and find the nearest one and say that this is the class of that nearest vector, that nearest document is the class of the new unlabeled object. And the generalization of this is that instead of looking at just one nearest vector or object, we would look at the k nearest ones. And then the class of the unlabeled object, the unlabeled document, would be the majority class among the k nearest neighbor. So if you find that if your k is 7 and you find that 5 out of the 7 nearest vectors are of class China, then you assign China to the unlabeled object, to the as the class of the unlabeled object. And again, the idea here is that why would this work? Because we have this contiguity hypothesis, we can expect the test object OI that we want to classify to have the same label as the training objects in the local region. So we said that classes make up sort of contiguous regions in the space. So when we want to classify a new object OI, if its neighbors are of some class, then it's probably also of that class. Defining the parameter k, so how many, yeah. Yeah, that's true. So what you're saying is basically, I'll just jump ahead, is something like this. So let's say we have these blue and yellow points, and if our k is 1, so this is the region that you're saying that this is, if a new object happens to be in this small region and our k is just 1, it will be of the blue type. But if you look at the bigger picture, it seems like the yellow ones are sort of the points that are on top and the corner there, and then these one are the blue ones are in this corner. And but for some reason, as you said, for some mistakes or noise, some blue points ended up being there. So one way to sort of accommodate this noise is to have a large k, for example. But of course, the algorithm itself has its shortcomings, which we will come to. But this is a legitimate concern: is that what if we have a small k and there is noise in our data, then we'll end up with something like this. But let's come back to that later. Yeah, so and then the parameter k itself is not defined. So there is no predefined value of what is k. It is something that you have to specify, mostly by trial and error. So normally in a normal setup you would have your data set will consist of train and fine-tuning, so train set, fine-tuning set, and then test set. So you train on, and in this case you actually don't train, you just memorize the vectors, and then you try with different k's and you see, okay, 3 gives me 50% or 60% accuracy or recall. We haven't talked about evaluation yet, but just jumping ahead. So basically trial and error, looking at trying with different numbers. If you get the good accuracy, you say, okay, this is the good k, I'm going to go with this. That's a disadvantage of the algorithm, of course, but it's a very powerful algorithm, and it's actually very powerful when you have classes that are represented by different prototypes. So they sort of, in a sense, have different prototypes, not just one, like conceptually. So K and N has been used quite a lot with handwriting or handwritten digits recognition. So automation of like the distribution of letters when you write the zip code or the postal code, and you have it handwritten, and recognizing the numbers itself. The way you write the 0 or the 1, there is no prototypical one. There is the typer one, like the computer-based one, but people tend to write it in many different ways. So K nearest neighbor would work in this situation. Yeah, and sort of as we mentioned before, Rocchio is based on just the boundaries based on the centroid, whereas in K and N the decision boundaries are determined locally. And this decision or these decision boundaries can be explained or viewed through something called Voronoi tessellations. So what are these Voronoi tessellations then? Voronoi tessellations, let's forget about K and N for a second. So Voronoi tessellations is this tiling up of space using geometrical shapes or polygons in this case. And in each, so if these dots are the points you have, these solid dots, each cell of these cells consists of the points that are closer to the dot within the cell than any other dot in the space. So these are the way, this is the way they are computed. And so whatever point that is part of a given cell, we are sure that its distance to the point within the cell, this solid point, is higher than, or it's smaller, sorry, than any other solid points within this shape. So when you have a K1 nearest neighbor, and these are your data points, so these are the documents represented in the space, the decision boundaries are based on the Voronoi cells here, and this is a one K equals 1 representation of the decision boundaries. If K is higher than 1, then the Voronoi cells will be the set of points whose K nearest neighbor is the same. This is just a visualization of the of the decision boundaries that are drawn if you have K nearest neighbor. But these are decision boundaries per data point. What we want is actually a decision boundary per a class, not the per data point, right? So this white line here is actually the decision boundary between the diamond class, the circle, and then this one here between the X and the circle. And the decision boundary then is this is following the boundaries of the Voronoi cells that are of different types. So if you have a Voronoi cell of type diamond and a Voronoi cell of type X, you start drawing the decision boundary here. What matters here in this picture is that, as you can see, the decision boundary here is complex. It's not linear anymore. It's not just a line. It's this shape that is you can only get if you have a nonlinear classifier. If we have this star that we want to classify, if we have one nearest neighbor, then it's going to be classified as a circle. But if we have three nearest neighbor, these would be the three nearest neighbor, and then two x's will make a majority class, and it will be an x. This is, yeah, this sometimes is counterintuitive to sort of to look at, but it's simply just a visualization of what kind of boundaries you get per data point and then per class. And yeah, so if we go back to this figure here where we have we're looking at the effect of k. So if you have k equals 1, and these are your data points, the orange or the yellow are in are one class and the blue are another class. If you have k equals 1 only, you end up with a decision boundary that also includes so-called islands. So, and it's so clearly not ideal, because this is what we refer to as an overfitting case. So your classifier is overfitting the data, trying to learn every single object, without taking into consideration that your data might be noisy, that some members or some documents, for example, if we're talking about document classification, might be far away from the original distribution of the class. So if you increase the k to be 15, then you have a more reasonable or meaningful decision boundary. So we are willing to take a decision boundary that's that includes some mistakes, rather than a decision boundary that is so specific that is clearly not generalizing. So the aim of machine learning in the end is to generalize, to be able to learn, to abstract over the data and have a generalized view of the patterns, for example, of the data. So if you just look at single objects, you are not trying to learn a pattern or a distribution, you're just memorizing it. What happens if we make kn? So if we make n being the number of training examples we have in our data set, what would be the result? Yeah. Yeah, always most common class. So that's what we call majority class, sometimes used as a baseline to compare classifiers. So assign an object to the majority class all the time. So if your majority class is 56%, then you are 56% of the time correct. Let's say, yeah. Yeah, we can take k and n classification a step further by introducing a probabilistic version of the algorithm. So again, this is our A and B classes. We want to classify X, and we are working with 5 nearest neighbor. So in the KNN algorithm that we just introduced, the class of X will be A, right? Because we have 3 neighbors of class A and 2 of class B. The majority class is A. But we might want to actually say that the membership in a class is can be determined by the proportion of the k nearest neighbor in C, meaning we want now to shift from hard class membership to soft class membership and probabilistic class membership. So now we can say, no, so now I don't have the numbers here, but anyway, so out of the 5 nearest neighbors of X, there are 3 that belongs to class A. So that would make 0.6 of the total number, and 2, right? Yeah, I think so. And 2 in class B, so that's 0.4. So then we say that X is 0.6 of class A and 0.4 of class B. So that's one way of introducing probabilistic membership functions to K and N. Another way of doing this is to introduce distance weighted votes. So depending, again, if you look at this picture here, it's clear that the 2 B instances are closer to X than the 3 A instances. So what if we introduce the similarity or the distance that we can compute between X and B, X and its nearest neighbors to the equation, and then use that to determine the class. So then we can say we will introduce a score for a given class Ci that can be computed as the similarity. So this equation is just sometimes confusing. So what's happening here is that for each class, in this case A and B, we want to compute the score of an object, unlabeled object, OJ, being a member of this class. Okay, so for each vector xn that is member of the k nearest neighbors of our unlabeled example, we will, for each one of these, we will sum the similarity between xn being the nearest neighbor, one of the nearest neighbors, and xj being our x. And if so, and similarity, of course, could be defined in different ways, as we discussed before. And in order to make this equation general, we have this check function here that checks if xn, the current nearest neighbor, is member of the class ci that we are scoring. If it's member of that, then it's 1. If it's not member, then it's 0. So just this is just to this part here, just to make the equation general. So for because we know that we have different classes and the nearest neighbors could belong to different classes. So if you're looking at class A, we want to make sure that when we compute the score, we are only looking at vectors that are of class A. And then when we compute the score for class B, we want to make sure that again the vectors are of type class B. And this actually, yeah, one thing I didn't mention is in this way would help give accurate results and also help resolve the ties. So if you choose your k to be an even number, you will end up with cases where you have two neighbors of one class and the other two of another class. So you normally want to choose it of an odd number. So you will have a more sort of you won't have the problem with ties, being that the nearest neighbors having equal distribution. Assuming that we are doing binary classification. Of course, if you're doing classification on multi-classification, then 9, an odd number could of nearest neighbor, 9 nearest neighbor could be 3, 3, 3, belonging to 3 classes. But we're looking at, in this case, binary classification, only 2 classes. Yeah, so oops. Not you don't. Yeah, so it's you don't necessarily avoid it. Of course, I mean it makes it less likely, right? But it's not a guarantee that you're going to avoid ties if you include scoring, because it might as well, as you said, either 2 points, for example, that are not very similar, not very close, but their sum will make them as close as one other point. But the likelihood of ending up with that situation is now smaller than just with pure and k nearest neighbor calculation without any addition. Any other question on this part? So summing up what's or sort of looking again at k nearest neighbor, as you can see, there is no learning at all happening here. So what we are doing is we are looking at the examples in the training data. At least in Rocchio, even though we don't do also much of a learning, but there we compute an average vector, a centroid, that is representative of the data. Here we just memorize everything. All the training examples are part of our model, which means that as we talked in the beginning, in general in machine learning, the more the merrier. So the more data you have, the better your model will get. In this case, the more data you have in a k nearest neighbor, the less efficient or the more costly or will be the computation for k nearest neighbor, because what you are doing when you classify is that you're comparing to all the training examples you have. So the test time is linear in the size of the training set. So if you increase it to a large number, then it might be impossible to actually finish compute. Well, not impossible. It takes a long time to finish computing. You have a question? Yeah. But the idea is, how do we actually find the 3 nearest neighbor first? You pick 3 random points and yeah, I think there are ways to heuristics to actually go through the data set of points that you have. But there, as far as I can tell now, is you will have to look at all the points to get the optimal result, at least. But there might be, I don't know actually, there might be other optimization where you can split your vector and space in a way that so that you can look at certain points. And yeah. But it's in this implementation where we don't have any optimization, the time complexity is dependent on the number of instances in our training data. But it's independent of the number of classes. That's a distinction. So Rocchio is dependent on the number of classes, right? Because for each class you have a centroid. So the number of computations you do is dependent on the number of classes. So if you have some problem that is for some reason has so many classes, KNN might be a better solution in terms of time efficiency. Yeah, this is again, if we think about the IR introduction and that we want to return the K when you do a search and you want to find the most relevant documents to a query, this is basically a k-nearest neighbor problem in a sense, because you're looking at the most relevant vectors. So it's just an aside. Also, we don't have actually much time to talk a lot about that. I thought I would actually, because I mean there is still time for assignment 2B. You're still just starting with assignment 2A, but it's natural to introduce it here. So this assignment you will work on in 10 days, I think, or so. So in 2A, what you're doing is that you're building this vector space representations for a set of, I think, 120 or 22 words based on features, bag-of-word features you're extracting from a sample of the Brown corpus. In 2B, what we will do is we will provide you with class labels for these 120 words, or for most of them. I can't remember the exact number, 120 or 122 anyway. If you have looked at the assignment, you know what I'm talking about. I'm not sure if everyone is following. So assignment 2A will include a text file called words.txt, which has 1 word per line. These are the words I'm referring to here. And your task in 2B would be to train a Rocchio classifier that predicts the label of some of these words. So some of these 122 words will be unlabeled. But you will be using the vector representation that you actually made in 2A to actually do this computation. So very quickly, before we run out of time, so these are the words that you already have in words in the file now. They will be in the next assignment, they will be labeled with the semantic concepts, abstract concepts, food, institution, title, place name, person name. Some of these words will be labeled with unknown. And your task would be to build a classifier, a Rocchio classifier, that assigns one of these labels to each of the unknown examples. Okay, so there was a part about evaluation. We'll have to take it next week. So next week we will look at clustering, mainly on C-means clustering, but we'll also have to look first at how to evaluate a classifier. When do you say a classifier is good, and what are the different measures for evaluation? Yeah, I think that's it for today. Thanks.